Okay, before we get started here, I actually realized that I forgot there was one more thing I was going to say about specific heat when we can assume ideal gas behavior. One other little thing besides specific heats are a function of temperature alone. There's a relationship between Cp and Cv that holds only for ideal gases. Cp is equal to Cv plus the gas constant R. Okay? So the relationship between Cp and Cv, the difference between Cp and Cv, is the gas constant R. I want you to accept this for the moment. Just accept this for the moment and I will prove it later. It has something to do with this boundary work that is the distinction between Cp and Cv. You can actually calculate the boundary work and therefore for an ideal gas and therefore get this expression Cp is equal to Cv plus R. But for the time being, I think you should commit it to memory that for ideal gases, the difference between Cp and Cv is the gas constant. Okay? All right, let's move on and do an example here. Let's do a nice simple example to get our feet wet. We have a rigid container containing air, a mixture of nitrogen and oxygen, air. Initially, this system starts off at a temperature T1, and then we add heat, Q1 to 2, and we heat the system up to T2. T1 is equal to 300 degrees Kelvin. T2 is equal to 600 degrees Kelvin. I want to know how much heat is required per unit mass. Lowercase q. How much heat is required per unit mass, Q divided by M, to raise the temperature of this air contained in a rigid container from 300 to 600 degrees Kelvin. I want to know how much heat is required. Okay? All right, so how are we going to proceed here? Well, we're talking about specific heats, so we better use specific heats. We are, after all, on chapter 3, which is specific heats and energy interactions, so analysis. Let's write down the definition of specific heat. Which one? Cp or Cv? What process is this? We're adding heat from state 1 to state 2. What kind of process is this? Rigid container? Well, that means presumably constant volume. Isochoric process. Isochoric process, volume is constant. So let's write down the definition of Cv. Cv is equal to the little bit of heat transfer divided by the mass of the system divided by the temperature change due to that little bit of heat transfer. Let's solve this for Q. Little bit of Q. Del Q is equal to Cv m dt. Okay, so all I did is I solved for del Q. Now, del Q is an infinitesimal or differential heat transfer. I want to get the total heat transfer per unit process from state 1 to state 2. So I think the second thing I'm going to do is I'm going to divide both sides by the mass of the system. If I divide both sides of the equation by the mass of the system, the del uppercase Q becomes a del lowercase q. Del lowercase q. So I have del lowercase q is equal to, the m's cancel out, and I get Cv dt. All right? Now, I want to get the overall heat transfer lowercase q1 to 2 per unit mass. How do I go from a differential process involving del's and d's to an overall process? I have to integrate. Let's integrate this thing over the process. 1 to 2. Temperature, dt, is the, well, variable of integration is T. So I'm going from T1 to T2 here, okay? The quantity on the left is going to be the overall heat transfer per unit mass, Q1 to 2. So I end up with Q1 to 2 is equal to the integral of CV dt. Now what do? We need to integrate this. If I knew the functional form of CV, I could integrate with respect to temperature. I don't know a lot about CV at this point. And remember, we're integrating from T1 to T2. Air in a container. Maybe I can assume ideal gas behavior, and then maybe CV is a function of temperature alone, and then maybe I can show you some tables to extract out CV, okay? And we can perhaps integrate this integral. Let's see if the ideal gas equation or ideal gas behavior is valid for our air. Let's see if the ideal gas law is valid for our air. So T reduced. Remember, ideal gas law is valid when T reduced is greater than 2. So the lowest T reduced value is 300 K. T reduced min is equal to T1 over T crit. So what's the critical? Let me do a share here. What is the critical temperature for air? I thought it was like 1, oops. So what? Air, 133 Kelvin. 133 Kelvin. So I have 300 degrees Kelvin divided by 133 degrees Kelvin. And that's about 2 point something. 2.25. 2.25, which is greater than 2. I don't know anything about the pressure. Critical pressure is pretty darn low for air. I'm sorry, high for air. So if you look here, 37.7 bar. So reduced pressure needs to be about 0.2 or less. So because the critical pressure is so high, for most workable pressures, I would say it's quite plausible from an engineering standpoint that our reduced pressure is going to be less than 0.2. So I'm not going to make too much of a song and dance out of it. I'm just going to write here under my assumptions, I, G, B, valid. We can treat the air as an ideal gas, IGB valid, okay? And therefore, CV is a function of temperature alone, and so CP, but we're interested in CV. Function of temperature alone. Okay, so CV is a function of temperature alone now. It is a function of temperature. So what is CV? It varies with temperature. It's a function of temperature. Let's have a look at some values of CV here for air. Okay, so let's go back to the appendix here and let's look and see if we can find specific heats, a table of specific heats. Table B8. Here's specific heats for solids and liquids. Remember CP and CV were the same for solids and liquids, in other words, incompressibles. So here we have CP values as a function of various temperatures. So CP and CV typically vary with temperature and other stuff. For solids and liquids, they're a function of temperature, and they're the same. CP and CV are the same. And now we have ideal gas specific heats, various gases. Air, temperature, CP, CV. At 300 degrees Kelvin, CV is 0.718 kilojoule per kilogram degree in Kelvin. 600 degrees, 0.764 kilojoule per kilogram degree in Kelvin. Okay? So specific heats over our process as the system heats up from 3 to 600 is changing a little bit. It's going up by about 0.06, 0.05. It's increasing by about 10% as the system heats up. So CV is not entirely constant during the heating process. It's getting bigger as temperature goes up. So what are we going to do? We're going to evaluate our specific heat at the average temperature, 450 degrees Kelvin. So what we're going to do is the following. This integral is approximately equal to CV evaluated at an average temperature. What's the average temperature? It's 600 plus 300 divided by 2. That's Kelvin, or 450 degrees Kelvin. Okay? What can I do with a constant or average specific heat? What can I do with it when it's in an integral? This guy is now a constant value evaluated, CV evaluated at 400 degrees. Let's pull it out of the integral. CV T average evaluated, that's 450, times the integral of dt from T1, running out of space here. dt from T1 to T2. Integral dt from T1 to T2 is delta T. So I get CV evaluated at 450 degrees Kelvin. Delta T, or if you like, CV evaluated at 450. T2 minus T1. Okay, so the heat transfer. Let's write that down over here so we can start fresh. The heat transfer per unit mass over the process, Q1 to 2 is equal to CV evaluated at the average temperature, which is 400 degrees Kelvin, times T2 minus T1. Now, we've chosen to average the specific heat, so maybe we better put that in our assumptions. CV is equal to CV at T average. Okay? So we're going to evaluate the specific heat, make it a constant so we can pull it out of the integral, and evaluate it at the average temperature. Okay? Let's see here. Let us get the value. CV at, for air at 450 degrees is 0.733. 0.733, and that has units of kilojoule per kilogram degree in Kelvin. And my temperature change is 600 minus 300, T2 minus T1. So we have 600 minus 300, and that all has units of degrees Kelvin. Notice the kelvins cancel out. The specific heat and the temperature change. And I get 0.733 times 300. $219.9 kilojoules per kilogram. 219.9 kilojoules. Oh. Sorry about that. There we go. 0.733 kilojoule per kilogram degree in Kelvin. Our temperature T2 was 600 degrees. Our temperature T1 was 300. How much heat to raise the system from 3 to 600 degrees? 219.9 kilojoules per kilogram. Notice the kelvins cancel out. So Q, lowercase q, Q1 to 2, which is the heat transfer from state 1 to state 2 per unit mass, is equal to 219.9 kilojoules per kilogram. Box it up. Done. Over. First use of specific heats in a problem. How to calculate the heat transfer to heat up air over an isochoric process. Okay? Now, one little thing I want to point out before we move on, because you will have an opportunity to do this kind of a problem in a slightly different way. We assumed constant specific heat to do this problem. So we assumed a constant specific heat, a specific heat evaluated at the average temperature, so that we could pull it out of the integral and evaluate the integral to get the heat transfer. That's why we assume constant specific heat. And if you looked at the tabulated values for specific heat, they don't change that much. So here, let's go back and look. Specific heats for constant volume process, again, 0.721, 0.776, about a 0.055 kilojoule per kilogram degree in Kelvin change. About 10% variation between 300 and 600 degrees, about 10% or less. So we would expect our heat transfer calculation to be within 90–95% accuracy. What if you want very, very good accuracy for your calculation? Let's say you want maximum accuracy. Well, look at this. Table B9. Ideal gas polynomial expressions for specific heat. Cp over R, so this is a dimensionless quantity. Remember, universal gas constant, the gas constant R, had units of kilojoules per kilogram degree in Kelvin. So does specific heat. So Cp over R is dimensionless. Cp over R for various ideal gases can be expressed in a fourth order polynomial with coefficients alpha, beta, gamma, delta, and epsilon for the coefficients. I could have done this problem. I'm not going to. I'm going to leave it for you to do it for a homework assignment. I could have done this problem by substituting this polynomial expression into my integral and then integrated. Okay, I could have integrated. The values for the coefficients, alpha through epsilon, are given by these columns here. Note, for the various gases, here's air. Alpha is 3.653 for this polynomial curve fit for specific heat, Cp. Beta, negative 1.337 times 10 to the negative 3. So beta times 10 to the 3 is this value. Gamma, this value times 10 to the negative 6. Delta, this value times 10 to the negative 9. So all these coefficients get progressively smaller by 3 orders of magnitude as you move up in order in the polynomial, okay? So another way to do this using variable specific heats by the equation in table B9 is to substitute this expression into your polynomial, into your integral, and integrate with respect to temperature. Plug in the various temperatures, plug in the various coefficients, and you get the heat transfer. You'll have a homework assignment involving comparing a constant specific heat versus a variable specific heat using these polynomials for a heat transfer calculation. All right, ladies and gentlemen, I think that's all I'm going to say today. I think we've done enough. We're going to move on to the first law of thermodynamics. In other words, the energy balance. We'll make it a short lecture for Wednesday, given this is a little bit longer lecture. We'll finish up on, we finished up heat and work. We're going to move on to the energy balance tomorrow. Take care, ladies and gentlemen.